Okay. All right, we'll go ahead and get started. So hi, everyone. Welcome to the head seminar this week. My name is Amy Gall. And this semester, the organizers are myself, Federico, Carolyn, Andrea, and Anna. So first up today, we have Yeimy Rivera. So Yeimy received her bachelor's degree from UCLA, her master's from California State University, Northridge, and her PhD from University of Michigan. She became a future faculty leaders postdoctoral fellow at HCO, and then recently she's joined on here at SAO as a research scientist in the solar physics group. Her research pertains to investigating the evolution of plasma from the sun by studying heavy ions in the solar wind and transients. She simulates the non-equilibrium ionization and recombination processes of charged states to investigate the thermodynamic conditions that reproduce ion observations at the sun and interplanetary space. She's part of the Solar Orbiter's Heavy Ion Sensor team and Parker Solar Probe Suite team. And today she'll be talking to us about 3D MHD time-dependent charge state ionization and recombination modeling of Bastille Day coronal mass ejection. So take it away, Yeimy.
That's a mouthful.
That's a mouthful.
Quick question: how do you turn this on?
There should be.
Can everyone hear me? Yes. Okay. Yes, thank you. Thanks for the invitation to give a talk on a paper that was recently published, actually just or recently accepted rather, soon to be published. That I can send around at some point on the where we look at the evolution of heavy ions in a corona mass ejection. So essentially trying to recreate an event, the Bastille Day CME as it's called, since it erupted during the Bastille Day. And looking at heavy ion composition of that, trying to sort of connect the evolution from the sun to the particles that we measure in the heliosphere. And so this simulation that I put right on the title page is synthetic EUV emissions or reconstructions of the images that we saw in the eruption, which I think is pretty cool. That I'm not actually going to show or highlight in the presentation, but I think it's really cool. So I think most of us are fairly familiar with what a coronal mass ejection is, but one of the things that I wanted to highlight in this slide is the fact that we often see the CME, at least in the white light coronagraphs, that have this multi-part structure. Should I minimize that? Yeah. Okay, yes. Yes, so in sort of this white light coronagraph, we often see that it's not just a homogeneous blob of plasma being ejected out from the sun. We actually see a lot of structure associated with the coronal mass ejection, and we actually associate it with particle during its passage, particle detectors in situ. So you can see what I've labeled there as the leading edge, the cavity in the filament core, the leading edge being formed as it sort of compresses against slower moving coronal plasma. As it compresses the front, it creates this higher density leading edge that's followed by a cavity. And then the core is often associated with this thing called a filament of prominence associated with this cool structure on the corona. But what I wanted to highlight was that oftentimes these different structures have different properties, or different thermal structure rather. So the leading edge and the cavity part of the CME generally is generally very typical of coronal conditions. So multi-million Kelvin temperatures, fairly tenuous relative to the filament core. So here we see very highly ionized materials, sort of typical material that we expect in the corona. And then the filament core, this plasma, it's often seen as the brightest structure in the white light coronagraphs. That, as you can see, several orders of magnitude cooler compared to the corona itself, and also relatively denser. So much cooler, in fact, that we often see very low ionized material, sometimes even neutral material associated with that structure in the corona. So oftentimes we see the structure itself sort of suspended, magnetically suspended in the corona as these dark blobs. Generally in absorption, they're an absorption because they're absorbing UV radiation. They're actually not emitting in the UV. But oftentimes, one of the signs that we see that the CME after it is erupted, it starts to lift off from the corona, that it is being very quickly heated, is that the prominence goes from absorption to emission very quickly, just as soon as you start to see the eruption happen. This is really one of the ways in we know that the heating is happening very quickly, and really at the heart of uncovering those mechanisms, the mechanisms heating the plasma and sort of ejecting it out, accelerating out the plasma out at such high velocities, gaining so much kinetic energy, is really during these early stages of evolution from the sun. So from sort of this liftoff stage through these chronograph images. And so one of the ways in which you can try to constrain those mechanisms a little bit more, or a little bit better, is by kind of trying to reconstruct and examining properties of the eruption with sort of these individual events that are very well observed. For the example, as an example, the Bastille Day CB was very, very well observed across the heliosphere. So both from remote sensing observations and also from particle detectors that we're going to be talking about. So that is just the movie showing the Bastille Day in the UV, in this composite image with the white light. So the Bastille Day itself, of course, erupting on July 14th, Bastille Day, 23 years ago during peak solar maximum. So this is peak solar maximum, solar cycle 23. It was driven by a filament eruptions or a halo CME directed towards the Earth. You can kind of see it happening here. It's just happening and erupting just north of the center. And you can see it, and then immediately after, you see the energetic particles hitting the white light coronagraph, the detector, which is kind of this dramatic sort of it's what sort of fills the white light coronagraph. But so the Bastille Day was associated with an X class flare. So the association of the flares, the classification goes A, B, C, M, and X, and the classification is associated with the amounts or the peak of soft X-ray flux that you see. So it had the highest classification of flare. It was also clocked at roughly about 1,700 kilometers per second. So the leading edge within this field of view of the coronagraph was observed to be traveling at 1,700 kilometers per second. So as sort of a reference to other CMEs, the mean speed of a typical CME in the same range in this corona is between 400 and 600 kilometers per second. So very, very fast, very energetic, associated with very, very energetic or having fairly high kinetic energy, rather. But one of the things that I wanted to point out is that, as I was saying before, this is an event that was very well observed. There's actually 34 peer-reviewed articles associated with it, and ours being number 35, and I know of others that are also in progress, also looking at the Bastille Day CME. So as I mentioned, very, very quickly moving out of the corona, Earth directed, it was traveling so fast that it was able to reach L1 roughly about a day after 5 successive CMEs. So we see 5 successive CMEs, and then the Bastille Day measured right after that. So peak solar maximum phase, still traveling about 1,000 kilometers per second. So the plot that I'm showing here is just a stack plot of all of the observables from Bastille Day at L1, measured by the Advanced Composition Explorer. So the top 4 or 5 plots are showing the compositional signatures of the CME, and then where the top, for instance, these are the relative abundances of carbon, oxygen, and iron here. So for instance, this is carbon 4+, 5+, and 6+. And then the bottom 4 panels are showing the bulk properties. So the the proton temperature, the bulk speed of the plasma. So you can see traveling still over 1,000 kilometers per second at L1. And then the density, proton density, and then the field components of the, so the magnetic field components and the magnitude. So one of the things that we see from the magnetic field component is that you see this sort of sheath kind of variable magnetic field towards the beginning. That's called the sheath component. That's generally associated with the leading edge that we saw in a couple of slides back.
Following that is a large curvature in the magnetic field that's generally connected to a flux rope, the passage of a flux rope. The magnetic field components of the happen to be directed in south direction, which is essentially an ideal orientation for day-side reconnection at the sun, at the Earth rather. It sort of drove this very large geomagnetic storm that's described in this paper here. But as I was mentioning, so this event has 34 publications. One of the things that really hasn't been explored in the past is the ionic structure during its passage at L1. So essentially the panels that we're going to be focusing on, which are these three panels here. And the reason why that's of interest to us is because it really does, the ion composition that we measure is really, it can tell you a lot about the early stages of evolution of the CME. And the reason for that is because the reason why heavy ions are really a great diagnostic of the thermal history early on is because they're a direct reflection of ionization recombination processes taking place early on. So as the plasma starts expanding, the density drops very, very quickly. Ionization recombination essentially become less and less effective farther and farther from the sun. So what happens is you have ions that essentially remain, ion ratios and ion distribution profiles that remain fixed at some point away from the sun. In this case for CMEs, it happens to be fairly close to the sun. And this is just a visual representation of the freezing process. So happening below 15 solar radii or so for most ions. And so what happens is that the charge states that we measure in the heliosphere, so the ones collected with instruments like SWICS, are a direct reflection of the cooling and heating that's happening up to the freezing point, which is really interesting for us because we can measure those really well with particle detectors. So for the work itself, what we tried to do is try to reconstruct these two general structures that we see during the passage of the CME. So the yellow box and then the orange box, the first half of the CME. So in that yellow part of it, we see very highly ionized, when we sort of focus on the iron distribution, very ionized charge states. We see the presence of iron 24 plus consistently across this entire period. And then the plasma itself has an average iron charge state of about 16. That is very high for plasma. Generally, for CMEs is between 9 and about 13 or so. So fairly high compared to CMEs itself, very energetic, highly heated. And then the second half, and I forgot to mention, so this part here is associated with that flux rope that we were talking about before. And then the second half, we see a very common iron distribution, this very bimodal feature in the iron distribution, where we see a peak in the iron 16 distribution, which is up here, and then a peak at a lower ionized state. So here, so apart from the double peak distribution, we also see the presence, towards the beginning of the box, of lower charge states that are generally not often seen in coronal mass ejections, potentially connected to the prominence of the material, the prominence of material that we were talking about before. And so the goals of the work. So first, this is the average charge state of carbon, oxygen, iron that we're trying to reconstruct. So this is just another view of the two boxes there, just averaged, which is what we're trying to reconstruct for the two different sort of types of plasma that we see. But the goal of the work is then to examine these two periods to really understand the origin of the plasma. So where this originates from, the different structures that we see in connection to the structure that we see in the sun, or UV and white light images, for instance, determine the conditions that form these ions, and then try to identify the energy source within the evolution of these structures that actually reconstruct the observations, and try to potentially determine missing drivers for some of the profiles and highly ionized material that we see in the observations. So like I mentioned, this is a MHT simulation that was done by the Predictive Sciences group from using the magnetohydrodynamic algorithm outside the sphere, MOS MHD model. So details of the MHD code and also the simulation setup, the pre-eruptive sort of flux rope structure that they insert into the corona, all details can be found in this 2018 paper. In the interest of time, I'm just going to go over just very in general terms, what that work did, which is essentially just try to reconstruct the Bastille Yeimy as best as they could. They started from this stable pre-eruptive configuration in the corona. They drove an eruption through the coronal domain that was then coupled to this heliospheric solution and sort of propagated all to L1, so near the Earth, so they could compare both the remote sensing and in situ observations of Bastille Yeimy. And so very quickly, generally, they did a fairly good job at reconstructing the Bastille observations. So the general morphology and the white light and UV emission with them really well. So the general morphology is caught or reconstructed very well. Also, the bulk properties. So as they sort of propagated the plasma and simulated its passage at L1, they did a fairly good job at reconstructing some of the bulk properties of the temperature, density, and velocity, but also some of the field components as well. So generally, did a fairly good job at reconstructing the CME itself. So for our purposes, what we're really interested in is taking those coronal solutions in the coronal domain and coupling it to a time-dependent ionization code, a non-equilibrium ionization code, in order to sort of follow the formation of individual ions sort of evolving within the CME structure and sort of expanding in time and space in connection to the observations that we see at L1. And so the equation on the right is what's it drives the formation of different ions with ion populations in the glass themselves. The ionization recombination processes are they're sensitive to the electron right interactions with electrons, so they're highly sensitive to the electron density and to the electron temperature, but also highly sensitive to the bulk flow of the plasma. And the reason for this is because the bulk flow governs how fast things are happening, or how fast plasma is evolving away from the sun, essentially. And I just wanted to highlight some of the model assumptions. So ionization equilibrium at the base. So we start with ionization equilibrium, assume thermal equilibrium. So our temperatures are equal, our electron and proton temperatures are equal. Maxwellian distributions for the free electrons, and then so no differential flow. So all of our ions are flowing at a single speed, and single ionization transitions at a time. Okay, so what we have done is then taken what are called these tracer particles in the simulation that essentially follow the evolution of particular structures in the CME. So that way we can take one of those tracer particles and kind of go and take a look at the thermodynamic and ionic evolution within these very specific structures that we designate. So for instance, what I'm showing here is I've selected the initial condition of the tracer particles being very similar to what you would expect the prominence material to be of the sun. So very cool, very dense, like we talked about. And in this case, these are the particles that actually make it out to the simulation box edge. So conceivably, structures that would be measured by particle detectors in the heliospheres are actually making it out of the simulation box. And then also the ones that are heated to over 1 million Kelvin. So very specific conditions. And then we can go and take a look at what those charge states look like. So we have those two structures that we were trying to reconstruct. So I'll start with the second half because that's the one we actually reconstructed quite well. In this case, I'm actually taking one of the tracer particles from the slide before. And here, in this case, this particular thermal history of this tracer particle within the prominence material that gets heated up very quickly and starts full actually did a really good job at reconstructing the bimodal feature that we often see in the iron distribution of coronal mass ejections. So these are the simulations here that I'm going to show. The top three, so this is the carbon, oxygen, and iron distribution, and then the associated temperature density and bulk flow of that plasma, that structure in the CfA, and then the bottom three are showing the same thing as the top three plots, the relative abundances as a function of distance away from the sun and then evolving in time. It's a little hypnotic, so I try not to do it while I'm talking. But so what you see is the initial conditions in this case for this tracer particle, very cool, very dense at the beginning, right at the sun. And then we see this plasma very quickly heating up, starting to expand, accelerated to over 2,000 kilometers per second in this case. You can see that being reflected in the charge states as well. And then the bottom, you can see the evolution of the different charge states. So generally what we see is this evolution was able to reconstruct that double peaked distribution in the iron. So you can see, so at the edge of the simulation box, this would be where our freezing generally happens. And the ions that we see here are the ones that are likely going to be measured by the particle detectors. So our freezing ions look like this. So we end up with this double peak distribution in the iron. What's happening is, if we sort of go back slowly, we see initial evolution showing us there's rapid heating over 1,000,000 Kelvin very quickly. We start to ionize up to iron 16. It doesn't really go any farther than that. Iron 16 has a very high ionization potential, very hard to ionize past that, not enough, the temperature is too low. Then we begin to see the plasma cooling and expanding, and we start to see this cascade of recombination in the iron. You can see it really well in the iron. And what we end up seeing is that you get this peak at iron 16, iron 16 also having a time scale that's a little bit longer to recombine than the neighboring ions. And so we get a peak at iron 16, we also get a peak at a lower ionized iron charge state. What we found when looking at kind of surveying the parameter space for the prominence is that the second peak is generally formed by depending on how long this plasma has to recombine. So if you have freezing that's happening earlier, the charge state and this peak here is going to be at a higher value compared to if you have something that's recombining a little bit longer. Okay, so I'll jump into the second example. I'll just run this one because I have 3 minutes to go. But so in this case, what we see is kind of in a similar way. We see plasma starting off really, really cool, fairly tenuous, very coronal-like, that's heated up and then have less time to recombine, generally giving us a value, an average charge state of iron that's roughly about 13. If you remember, average iron charge state we saw was around 16. So essentially, the simulation really didn't produce any ions above iron 16 in a significant way. And the reason for that is because it really didn't reach the temperatures that would significantly, especially for something like iron 24 plus that we see in situ. Oftentimes, these are the properties, or this type of ionized materials is connected to flares. Those are typical conditions, right? 6 megakelvin above for the conditions that we see at flare sites. In this case, we weren't able to see that in the outflowing material. But the main point here was that, sort of coming back to the assumptions that we talked about earlier, we assume that the electrons are Maxwellian. We know that they are often not at flare sites. There could be a huge contribution of ionization coming from these ions or electrons in the high energy tail that we're not considering. We also took a look at potentially photoionization being important. It looks like it's really not, at least for ions above iron 16. So it sort of points to this idea that non-thermal electrons could be potentially important here. And we're really not considering that in the simulation. And then the last thing that I wanted to say was, so the heating that we observe in these two structures is coming from field line conduction via the heated plasma in the front. So we see this huge acceleration of the plasma. We form a shock. The speed of the plasma quickly exceeds the Alfvén speed, forming a shock very low in the corona. And so the shock plasma in the front, you get this field line conduction that generates all of the heating that we observe in the two structures. So the panels on the right are meant to convey that. The shock, we really see adiabatic cooling in our structure. a ton of adiabatic cooling that is combated by the field line conduction that we see, and very little radiated cooling or ohmic heating really in the two structures. Okay, so to summarize, what we see is that in the simulation, we were able to pretty accurately reconstruct the bimodal features that we see in not just the Bastille date, but other Yeimys as well. We were really able to reach any of the highest ionization states observed in the observations, potentially, like we talked about, non-thermal electrons playing an important role there for this additional ionization. It looks like the primary source of the heating that was able to reconstruct the double peak distribution very well was through this field line conduction via the shock plasma in the front. And we didn't talk about this, but we can if people like. The freeze-in distances that we see. So going back to the idea of where that freeze-in actually happens in the plasma itself, we see that this is much, much farther away, sometimes out to 20 solar radii for the iron, compared to what we typically see in the solar wind. So it's capturing, so at least the iron is capturing a lot of the evolution through the corona and the simulation domain. And so I'll end here and take any questions. Thanks.
Anyone has a question, I will run the microphone to you.
You didn't mention magnetic field orientation. Is there anything that you can trace that is some big recombination event that triggers the CME in the first place? Or then following it further out, you were talking about field line propagation, but is there more energy being deposited in smaller scale reconnection events that you can observe, to track, or predict?
Yeah, I think not in the simulation, but that could be additional, right? So additional localized heating that is not considered, potentially adding more sort of larger energy deposition than we're actually simulating dimension code. Yes, all of this could be potentially contributing to that. All we know is that we really weren't able to get to the temperature associated with the ionization states, but it would be interesting to test something like that in the future because we have very detailed observations of the CME. So could be interesting.
Yep.
Thanks, very nice. A question about the very first part of the evolution of the velocity and the ionization state. So I see that it seems there be just 2 points in simulation where after that the ionization state freezes at about 2.5 or 3 and then more or less settles on a value which doesn't change so much. So does it change if you if you change the beginning of this solution, the final state at the freezing distance of 20, or does it change the value of 20 if you change a little bit the resolution of this calculation, the delta R?
So you're saying if we were to look further out, or
No, if you look further, if you just increase the resolution for the ring.
Oh,
Because I see just 2
I see.
points.
Yes,
So
yes, yes.
right, just 2 points.
right? So this is the outputs from the model are taking at these very large steps, but the actual calculation is taken at a much higher resolution, like time resolution.
So it's
Which
just
we're not
that-
showing. Yes,
Okay.
exactly. That's a really good point. Because at the beginning, it looks like there's potentially a lot happening.
Yeah.
But all that is captured, it's just not specifically shown.
Okay.
That's a good point. Thank you.
Yeah.
That's another question. All right, anyone else? One more minute.
I forgot what was.
All right, if there's no more questions, we'll thank Yeimy again. All right, so next up we have Axel Donut. So Axel is a postdoc here. Please no close. All right, Axel is a postdoc here at the CfA, where he develops new statistical methods and open source software for the analysis. Yeah. that's not good. Okay, I'll continue. Again, so Axel is a postdoc here at the CfA. He develops new statistical methods and open source software for the analysis of astronomical low count data, with particular interest in galactic X-ray and gamma ray sources. Today he'll be talking to us about joint likelihood deconvolution of astronomical images in the presence of Poisson noise. So take it away, Axel.
Or is it working? It's off already. Okay, great. Thanks a lot, Amy, for the introduction. Yeah, I'll be talking about joint likelihood deconvolution of astronomical images in the presence of Poisson noise. So there are a lot of elements in the title, but I'll go through them one by one, and you can see a little preview what we're actually talking about. So it's really about denoising and improving the angular resolution of low counts data. So just a few more little words about me. So as I said, I'm working as a postdoc, but I'm also a member of the CHASC Statistics collaboration here at CfA. And I'm also one of the lead developers of a package called GammaPy, which is a Python package for the analysis of astronomical gamma ray data. And you can find a lot of my work actually publicly on GitHub, and also some more information on my webpage. Okay, so this is just a visualization of the low counts imaging process. So what we have is somehow the sky, which is our ground truth, or the flux that we're actually interested in. We have some instrument to measure this, and in this case, a satellite. This has a finite angular resolution, so we only see the sky a little bit sharp. And this is straight here. Then also we have effects like an uneven exposure. So we point the instrument at multiple positions in the sky for a different amount of time. And this also affects the data. So you have a specific pointing pattern. So you see the imprint of the exposure in the counts data. And then finally, I mean, those instruments we're interested in here in high energy are mostly particle detectors. So like basically all of the data is then affected by Poisson, nonlinear Poisson noise. And what you end up is a counts image that might look like this. And like a lot of science can already be done on the counts image here. But it would be nice if we could actually reconstruct the original flux image. Yeah, maybe we can restart it.
Maybe you can do full screen instead the desktop. Okay.
Yeah, so it would be nice if we could actually reconstruct from the counts data more of the original flux that we're actually interested in. And the question is how to do this. This process is called unblind deconvolution. Maybe I can this a little bit.
And we want to remove this, right?
Yes. Perfect. So this problem is called the unblind deconvolution. Unblind means in this case, so the PSF and the exposure are known. Typically, those can be simulated or obtained from like empirical estimates. And then if I do some statistics and math, I might be able actually to recover a nice image of the sky and couldn't resist. So it won't look like this. But if we're doing it right, then we can at least can improve the signal to noise ratio of the data and denoise and make it a bit sharper. So here's the elephant question or in the room question. So why not just use machine learning? I mean, we now have like all these nice methods that can actually sharpen images, they can denoise images. But the application we are looking for here is very specific, right? So we are trying to apply it to astronomical data. So there's definitely a lack of training data. Astronomical images from X-ray and gamma ray observations are very expensive to get. There's also no ground truth. We just don't know what the image really looks like. We only have the data that we've observed with the distorted, that are distorted through our instruments. And then there's the specific technical details. So like standard convolution neural network architectures are not really suited for the deconvolution task. Because what you would need to learn is something like an inverse PSF kernel in the spatial domain. And this requires really like large kernels and adapted architectures. This was something that was shown by Xue et al. For Poisson data, this is always important. So we are in the low signature noise regime. So it's really important to specify actually the type 1 errors. This means like false detections. And for this, it's really important to actually keep track of the full likelihood and also get an error estimate for any kind of method that you apply. And this is not guaranteed for many machine learning methods. There are some that actually do this, but not for all. There's also a bit of a technical detail. So, for example, machine learning would need to learn information that is actually available a priori. For example, the Poisson statistics of the data, we just know that it's distributed like this. So this is something that doesn't need to be learned. This can be just put inside. However, there are approaches that employ, for example, transfer learning, so training a neural network on simulated training data. This has been shown to work, for example, for very specific source classes like galaxies, but also not really in the Poisson regime. Okay, so we go back to classical statistics. The method that I'll be showing is, let's say, like inspired from machine learning, but I'll talk about that later. So for the counts image, typically, this is the model that we have. We can assume a Poisson likelihood per pixel. And then we can actually, once we have a model to describe that image, we can evaluate the likelihood of the full image. What you then typically do is you take the negative log likelihood. This is in astronomy often called the CAS statistics. I think this is maybe known to, or maybe known to most of you. The actual model that we use is right now just very simple. So this is the flux image that we're looking for. This is the PSF model that we have, and then we just forward fold this to get an estimate for the predicted counts. What you can keep in mind here is that this X is actually an image, so it has like many pixels, and each pixel is an independent parameter in the model. So this is like a very high dimensional optimization problem. This can be solved then just using gradient descent. So you take the derivative of the likelihood, then you introduce some in machine learning terms learning rate or step size for the optimization algorithm, and then you can try to estimate your X here. An alternative method for this is called the expectation maximization algorithm. And this was actually proposed by Richardson and Lucy. And this is probably also maybe the term that you've heard before for deconvolution. I think one of the baseline standard methods is the Richard-Lucy deconvolution. Maybe you've also already used it in your work. So the problem with this Richardson-Lucy method is the following. So here I'm taking a look at multiple examples where I'm running this iteration of the reconstruction for a different number of iterations. So I'm starting from this image here. So this is just running for one iteration. So not much sharpening has happened yet. Then I'm running for 10 iterations. So this image is already considerably sharper. But then what happens at higher iterations is that actually you can see that extended structures in the image start to decompose. So the reconstruction that you get is very speckly. And this gets even worse for 1,000 iterations here. What's interesting about this is so this is a reconstruction here, and after you've convolved this with the PSF, so to get the predicted number of counts again, then actually all images look again very similar. And once you compare it to the data, so if you compute, for example, the residual counts, then actually all those reconstructions here lead like to a reasonable amount or like reasonable distribution of residuals. But the actual reconstructions look very different. And the problem here is that really they all show good residuals, but you cannot really distinguish just from the likelihood alone between those three cases. And this is called the ill-posed inference problem. And one approach to improve on this is including more prior information to the problem. So we call this like base to the rescue. So the objective function that we have see before. This is now extended just by a log prior term that only depends on X, so only the parameters that are in the optimization. This they called the log prior. And there was one method proposed like 20 years ago here at the Center for Astrophysics. This was called the LIRA method, which stands for low counts image reconstruction and analysis. And this introduced a very specific special multi-scale prior to achieve smoothness of the image on multiple scales. And this was really intended to solve this backwardness problem of Richardson and Lucy. The initial idea and implementation was by Ash et al. In 2004. Also, the model is extended a little bit more. So in addition to just having the flux parameters, you can also have like a background estimate, and you can take into account the exposure here. And then instead of just doing something like a gradient descent for the optimization, this was really changed to a sampling method. So you actually sample from the log posterior here at this slide. And this is very interesting because you can get more information. So instead of getting a point estimate for your best reconstructed image, you actually get a distribution of images. And this means you have an associated error, or you get a distribution of images and you can compute an associated error of your reconstruction from that information, which is very nice. Here's another motivation on image priors. So I think humans are very good of having prior information. So you can already see just from your experience that this is somehow like an unlikely image. This is just noise. There's no structure in it. You can see this is probably a more likely image. So there's some structure, but it's still very blurred. But intuitively, you know that this is very likely an astronomical image. And you have just learned that by looking at many images. So you just have like an intuitive, very good understanding of what an astronomical image should look like. However, like for example, learning the full probability distribution of an astronomical image, something like this, or images using deep learning is hard. I mean, you need like lots of training data, millions of training data. And typically, as I said before, there's just not enough training data. However, it could be used for like very specific cases. For example, I've seen a paper where people applied this to the Sloan Digital Sky Survey sample of galaxies. However, what remains is an approach of transfer learning. This means we can actually try to learn something from data from another domain. And this is what I'm trying to motivate here. So instead of trying to learn the distribution of the full image, we can try to actually learn the distribution of smaller parts of the image. So, and those are just called patches here. On the left side here, you can see just some example patches from an astronomical image. And you can see that there are bright spots. Some have more like an edge here. There's a bright spot in the center. There's now maybe a point source, a bright spot here. And one way to model this distribution of patches is just using a so-called Gaussian mixture model. So what we do is we split the training image, and right now this can be like any astronomical image. Typically, it should have like good signal-to-noise ratio. We can split this into patches of a given size. Typically, in this case, I'm using 8 by 8 pixels. And then I learn a 64-dimensional Gaussian mixture model. So each dimension of the Gaussian is corresponds to one pixel with a number of components that I select. Typically, it can be like 100 or 200, or like in literature, it has been shown that even sometimes like 30 or enough. And from this, I can actually train this Gaussian mixture model and compute. And this is also like very nice about this Gaussian mixture model. I can actually compute the full likelihood of this Gaussian mixture model. I can compute it analytically and also train it. Training for this typically happens with the expectation maximization algorithm, but there are standard implementations for this available, for example, in scikit-learn. So this is very well understood. In this case, the Gaussian mixture model basically works as a clustering algorithm. So this now here shows an example Gaussian mixture model that was trained on this set of patches. And what you can see is that it groups these patches into clusters. And those clusters typically represent like base structures in an image. So here's like a diagonal edge. Here's like a gradient. Here's a sharp edge in this direction. Here is another very sharp edge in this direction. Slightly different. Here the edges move to a different direction, or slightly to the right, and all these structures. So this Gaussian mixture model can learn the elementary or basic structures in an astronomical image. The initial idea of this is by Zoran Weiss et al. From 2011. So this was actually introduced for the reconstruction of everyday images. And then this was later applied to the event horizon, or to the reconstruction of the data from the Event Horizon Telescope by Katie Baumann et al. This is the so-called SHIRP algorithm, which uses the same approach. This is then how this Gaussian mixture model is used during the actual reconstruction. So the image that I would like to reconstruct, this is shown in the background here, is split into these overlapping small patches. And then for each of the small patches, I actually evaluate the likelihood of the Gaussian mixture model, and I do this for all 200 components of the Gaussian mixture. And then I can actually select which one of the Gaussian components is the most likely one for this image. I've done this for one example patch here. This is the one shown in red. So this finds like the 3 most likely Gaussian mixture components. So this is one number 105, 77, and 17. But what you can see actually what's happening here. So this is then the example patch projected on the eigenbasis of the Gaussian covariance matrix of this component. But what's important here is that you can actually see that it denoises. It works as a patch denoiser. I think this is like a very intuitive understanding of what the Gaussian mixture model here can achieve. But what's also important is that actually this adapts to the structure in the data. So you can see that the bright spots here still correspond to the bright spots here in the data. So in each iteration then in the reconstruction process, the current estimation for the reconstructed image is really split into these overlapping patches. Then for each of these patches, I choose the most likely Gaussian mixture component. And then I can sum up these best log likelihood values for all patches in the image. In this way, compute like an approximate prior for the total image. And the idea here is that really typically in astronomical images, pixels only need to know about their neighbors, let's say. And so the correlation is typically local because like astronomical images are typically self-similar and astrophysical processes are typically spatially constrained to a localized region. This is not absolutely true. I mean, of course, you can have like large supernova remnants where like even one pixel on on one part of the shell would be correlated with another one of the other part. But in general, I think this applies very, very well. And then this posterior is actually optimized along to get a maximum a posteriori estimate for the reconstructed image. Jointly, so this is now actually we introduce the concept of the joint likelihood. So this what I've shown now, this is all implemented in a Python package called JollyDeco. So this is just short for joint likelihood deconvolution as not Poisson noise. And joint refers in this case to a modified likelihood function where I not only have one observation, but I can have like multiple observations of the same region in the sky. And in this case, I have an additional sum of the likelihood that goes over multiple observations. If you're familiar with some machine learning techniques, this basically corresponds to the loop over data sets in machine learning. So you have multiple examples actually for the same thing. I've set up the implementation of this to be a bit more flexible, so I can not only work with a uniform prior, so this would correspond to the Richardson-Lucy case, but I can also work with these patch priors and possibly other priors. And I can also optionally reconstruct with this JollyDeco package, like an upsampled image, for example, to increase a bit even more the angular resolution. So the resolution of the reconstructed image does not correspond to the data, but it's upsampled by a factor of 2, for example. This is all based on the package called PyTorch for the maximum a posteriori estimation. And PyTorch has this deep learning framework where you can automatically track the gradients and then apply things like gradient descent or stochastic gradient descent to actually optimize your posterior distribution. What's also nice is that the algorithm then becomes scalable because you can apply it directly, for example, or run it directly on a GPU. The code for this is not yet public, but it will be available somewhere later this year under this URL here. To really test the method, we defined a test data set that has multiple scenarios. And the first one is scenario A. This is just a selection of point sources where the point sources are very bright at the top, and then they get weaker to the bottom, and then they also move closer together to the left. And then there's scenario B. This is like in a collection of point sources, and then there's an extended source nearby, just with regards to shape. Then there's scenario C. This has like a very weak underlying disk shape component. Then on top are point sources, and then we have like these jet-like structures. And there's scenario D with some point sources like a spiral. And the idea is really to see how well can it reconstruct those scenarios, and whether, for example, also there are things like, even if you have like preferred directions, for example, in your data. So, for example, these jet-like structures. Yeah, that was interesting. Okay. Okay. Let me just show you. No, there was one thing I wanted to mention in addition. So we've simulated the data for two instrument scenarios. One would be Chandra. This includes a point spread function of roughly like 2 pixels, or a sigma or a Gaussian point spread function with a sigma of like 2 pixels. And then we had a scenario for XLM. This is like 6 pixels of Gaussian sigma. In addition, the Chandra has like a smaller, Chandra has a smaller effective area of unity in this case, and the XMM case has a larger effective area by a factor of 5 compared to Chandra. And this is to test then the joint likelihood scenario. So these are some results just for the Chandra scenario. This shows you the data on the left. This shows you the ground truth. This shows you the Joly-Deco reconstruction with the uniform prior with 10 iterations. This corresponds basically to the Richards and Lucy case. Then the same with 1,000 iterations. Then there's this reconstruction of the pi-Lyra or Lyra method that I mentioned before. And then there's the Joly-Deco reconstruction using the patch priors, one from Zora and Weiss. So this is the one that was learned from everyday images. And then there's another patch prior that I learned from clean data, which is radio data with very nice resolution in the galactic plane. This is then run for multiple scenarios, and I think you can easily see that the Joly-Deco method with for example, with the clean prior here really leads to very nice reconstructions. Let me just highlight that a little bit. So this is the ground truth, where the point sources just have a single pixel. Then the Joly-Deco reconstruction with the uniform prior and 10 iterations, this has not really sharpened the image. For 1,000, it gets much better. But then if you take a look at the other scenarios, then it starts to make these sources very speckly. And this is exactly the effect that we've seen before, the same for this extended source and the spiral here. This is then the pi-Lyra method here. This also works very nicely for point sources, but it has a similar effect with the speckliness for the extended sources, albeit it's not as bad as for the Richards and Lucy case. So this already works nicely. The same here for the extended source and here. Then the prior here learned from the everyday images. You can see that the point sources are not very sharp, and I think this makes a lot of sense because point sources are not very common in everyday images, like I don't know, images of cars and landscapes, let's say. But it works already better in the case of extended sources, so it does not decompose those extended sources as bad. And as you can see here, and the best results I've achieved with the prior actually learned from astronomical images from the Gleam data. So you can see good compromise for the point sources, they're still sharp, and you can see like very good reconstruction for the extended sources. Also notably for example, this weak disk source that's underneath, and also if you have something like if there's like very like I don't know, and there's no preferred direction here, but it works like uniformly in these directions. Then we tried modifying the background level to really push the method to the limits. There are three scenarios. So the background first with 0.01 counts per pixel, then a factor of 10 higher, and again a factor of 10 higher until there's just 1 count per pixel. For background, I think this is like typically for Chandra, this is very high. But as I said, like we wanted to push the method to the limits. The results that I show for Jolly Deco here, again, use this clean prior and an upsampling of a factor of 1. The behavior that we found is mostly expected, so the reconstruction improves with higher signal-to-noise ratio. And this is what you can see here. So the signal-to-noise ratio improves from top to bottom, and it improves from right to left. Then you can see that then you can see, oops, I think this, no, I just accidentally switched the slide, sorry. So for the low signal-to-noise ratio, there's less sharpening. This is also expected, but you can see that it still does the denoising. Speed up a bit. But still, for extremely, I think this is the important part, high signal-to-noise ratio, it actually converges to the ground truth. Almost this you can see in this case, albeit there are some effects here. So, for example, this ring still decomposes into multiple point sources. However, this can be improved once you take into account more data. So in this case, I've combined the reconstruction of the Chandra and XMM scenario. And you can see actually that with this joint reconstruction, you actually improve also the reconstruction here in the high signal-to-noise regime with the ring. So the idea is that this larger XMM PSF actually maintains the pixel correlations across like a larger distance in the distance pixels, and really improves this backlinking effect. Here's one example of the method applied to real data. So this is a supernova remnant E0102. This uses I think like 28 Chandra observations taken with the ACES instrument. In total, this amounts to 110 hours, I think, of observation time. And you can check, for example, these example regions here. So here's the zoom A. So this is like a filamentary region. And this is the reconstructed case where you can really see that the angular resolution has improved. You can see a bit more details, for example, for these structures here. And everything is nicely denoised. Another obvious case is this point source here that is shown in zoom B. So here it's very weakly. So the color scales are actually the same for these images. So this is very weak here, and here like the point source really comes out, and the signal-to-noise ratio is really improved. Or here you can really see like much more details in the morphology of this region shown in zoom C. I did one little estimate where I've tried to make a bit more. It's not really scientific analysis, but try to quantify somehow like what's the improvement of the width of the filament here. So this is an example application. I did an error estimate for this by just bootstrapping the events that I had. So this is like a very standard statistical method, and this is shown as the true translucent band underneath the data here. I found actually that the error here is surprisingly small. This means, this is not fully understood, but it means that typically the reconstructions that you get from the methods are rather stable against noise. And my current theory is that this is really due to this prior actually adapting to the data in these patches in the image. What I found when measuring then the width of the filament here, that the full width half maximum was smaller by 30% compared to the measurement just on the counts image. And at the same time, it's less noisy and corrected for exposure. Just one last example. This is the same method applied to a supernova remnant from observed with the Fermi-Lat observatory. What's interesting about this is that this uses 4 different PSF classes. So there the joint likelihood is not multiple observations, but it's actually multiple PSF classes in the that were defined by the Fermi-Lat corporation. So it effectively corresponds to the quality of the data. And it also uses a patch prior in this case that was actually learned from the James Webb Telescope CAS-A image. Maybe you've seen that. But it was learned from the PR image, and the idea was just to learn like a very good signal-to-noise ratio data. So if you take a look at this, so the feature that you see here really line up visually with data that is known from other instruments. And there are like no obvious hallucinations in these, so like unreal features in the image, let's say. But I have to argue here with plausibility and just say like what you get here is a plausible image if you compare it, for example, with the Rosita data or the Hess data above 1 TeV. For comparison, this is the Fermi TS map. So this is typically the images that the Fermi lab collaboration shows. And this has like, of course, like first angular resolution in this case. Last remark on the benchmark. So this is the method applied to multiple sizes of images. What's important here that the typical runtime for a small image like 128 by 128 images is typically less than 10 minutes on a normal notebook. But I've tried to scale this method on a GPU, and there you can really apply it to small or to large images as well. So the runtime for an image of 1,000 by 1,000 pixels is still below 1 hour. So let me just summarize. So the method, Jolly-Deco's method for joint likelihood deconvolution of astronomical images. It uses this patch-based image prior to reconstruct a flux image from multiple observations of the same region of the sky, taking really the individual instrument response functions into account. Both the patch prior as well as the accounting for multiple observations at the same time really improve the reconstruction quality. There's some future work to be done. It would be really nice, I think, to actually extend this method to handle the spectral dimension as well. We've seen that the reconstruction, for example, for the Chandra and XMM scenarios was dominated by the Chandra. So you actually keep the high angular resolution. So adding data with lower quality, let's say, does not really hurt the result. It would be really nice to have that for the spectral dimension as well, that you could imagine combining data, for example, from Chandra with another instrument that has a better energy resolution and then actually obtain the good properties of both instruments at the same time. It would be nice to try different approaches for patch modeling. For example, in literature, this has been done using normalizing flows as well. One could extend the method to handle multiple flux components that you can try to separate, for example, point sources and extended sources in the same image. And currently, Jolly-Deco uses this maximum upper story approach to get a point estimate of the image. But actually, there's more information available. So one could get a generic error estimate from the likelihood function because it can actually be evaluated. But this is currently not what I'm using here. So I've just used the bootstrapping. In general, I think it would be nice to find more applications for this method. So if you have interesting science cases for applying the method, please just talk to me. Otherwise, the paper for this is in a preparation submitted to AppJ. Currently, the method is not open source. Once the paper is published, I'll make it open source and it will be available for you to use. And thanks.
So technically we're over time, so it doesn't even have to leave if you leave, but if you want to hang around and have questions, I can answer. No questions? Okay, there's also slots available if you want to sign up to meet with Axel or Yeimy on that. Thank you.
Thank you.
Michael, what you mean? Yes. I think you're using from V. Yeah. So this doesn't work so well with and you just captures the content.
Yeah.
No, to capture information.
It tries to capture local information. This is what it does with the small patches. The reason why I use clean data, in principle, I could use any data. So, for example, for radio data, a very similar method is used for PHP data, which is called the church algorithm. And there, I think they actually use, for example, they trained this stuff in Mixable, they trained it on everyday emails. So it shows like things like cars, like people or whatever. It is just to learn, okay, like a local distribution of the image and those patches. That includes things like address, like point sources, not so much on everyday images, but and things like corners, things like gradient and all these things. So this is the basic idea. And then it depends. So you want to learn this prior, you want to learn on high I just saw this clean data, which I thought was really nice. But in fact, it doesn't matter. So just for fun, I used, for example, this James Webb data because it's also like very good signal noise ratio. And this, and also like very high resolution, so I can get a large image, I can extract millions of these patches. So these are the main criteria. And that in the end, what I get out of roughly always very similar Gaussian. And then I use this in my reconstruction as a prior. So when I do the reconstruction, what I ask the reconstruction to do is really to stay locally close to these shapes encoded by the patches. So I cannot like arbitrarily reconstruct some structure in the image, but I say with this prior, the reconstruction, it has to stay close to these shapes that are encoded somehow with the patches. And this way I can achieve like a better reconstruction. I don't get this backhoe effect, for example.
So can you try?
Use like
Are you here at the CfA?
yeah.
Yeah. I'll take the one, see which one.
Quick question.
Yeah.
Have you thought about exploring the time dimension? Because that's-
Not yet. I mean, the time dimension.
I mean, it's all approximately statistical.
Yeah.
But instead of spatial, temporal.
I have a few thoughts about it.
Yeah.
I mean, the time dimension right now is implicit, for example, in the fact that I have multiple observations, right, that were taken at different times. And it was interesting because I showed this example where I applied this to Chandra data. And what I can actually, because the observations were taken at different times, I can actually see that the underlying flexibility changes with time. So I can see actually that the structural image moves. Right now,
So the image is moving.
yes.
Because of systematic effects with the telescope.
Yes, this is actually one thing. This is actually one thing that I can correct for with the method. So because I have these multiple observations, I have one variation of the algorithm where I include additional parameters. Namely, I allow for shift of the image per observation, and I allow for a change in the background norm per observation.
These are very interesting things.